Hey guys, sorry my last video got cut off because my camera switched somehow to a different camera. Anyway, we were talking about this problem set right here, okay? And I wanted to point out to you what these open dots mean. Okay, let me zoom in a little bit for you. An open dot means the graph doesn't exist at that point, but it exists all the way up to that point. Okay, so this guy right here, it's like point, and then that open point, it doesn't exist. So if you were to draw a vertical line here through this point, it looks like it hits the graph twice, but it actually doesn't because this point doesn't count. This is an empty space. So you're going through this empty space, and then you're hitting the graph once. So the graph, you know, it approaches this where this coordinate would be, but it never actually goes to that coordinate. It gets as close as possible, and then it skips down here. So this point right here, this solid dot is included in the graph, and this open dot is saying this space is not included as part of your graph. So this one would actually pass the vertical line test because, you know, you draw it and it's like, okay, hits the graph once, hits the graph once, hits the graph once, and then you're like, oh, does it hit the graph twice here? And it doesn't. It actually just passes through this space and then hits the graph right there. In this case, though, when you draw your line, it has two solid dots, and so you hit the graph twice, and so that's going to be not a function. So boom, boom. So you're using the vertical line test here, right? And don't forget that it says explain. So you want to say something probably about inputs and outputs, right? So in this case, I would say something like, no, it's not a function. The input -1 has two different outputs. And that's just an example. You could say the input of 2 has two different outputs or something like that. But you want to talk about, you know, inputs and outputs and the vertical line tests and things like that. So that's the first kind of set, is just telling if a function is, or excuse me, if a relation is a function or not. And depending on the way that relation is represented, you look for different things, basically. Okay. The next problem set asks about domain and range. So let's kind of talk about domain and range again just a little bit and some of the differences there. Okay. So let's go back a couple pages. All right, so example 4 is actually a pretty good example here of two different types of functions. Okay, what we have here is two different graphs, and one of them is like a bunch of dots, and one of them is like a line. Okay, so this kind of disconnected graph we have a special name for, and the name is discrete. It's a set of individual points. Okay, this guy right here, this kind of graph is called continuous, which is like a smooth curve or an unbroken line or something like that. Okay, so this is called a continuous function. And this one has spaces and this one doesn't, is kind of the difference. So you have to kind of take that into account when you're finding domain and range, because the way that we represent those types of functions is different. So going back to the definition, okay, the domain is the set of all possible values of the first variable. Remember, that's the input or x. So domain is all possible x values. Okay, the range is the set of all possible values of the second variable. Remember that that's y, or the output variable. So range is all possible y's. So when you look at the domain and range here, this relation, or this is actually a function, but it's also a relation. There's only 1, 2, 3, 4 points, okay? So when we are finding the domain and range, we're finding all the possible x and y values. So let's kind of list out what those are, and I'm going to grab a piece of paper so I don't have to write in the book. So this first coordinate right here is -4, 4, right? And this guy here is -1, 2. And this guy here is 2, 1. 2, 0, excuse me. And then this over here would be 5, -2. Okay, so when we're finding the domain, that's all the possible x values written in like a list, and they're usually written from lowest to highest. So we're going to look at all the x values, right? So -4, -1, 2, and 5. That's your domain. Okay, and that's what they have here. Okay, your range is the list of all possible y values, or all possible output values. So range, we're going to look at all the y values. Okay, and typically they put them in order, so you'll notice that we have, you know, 4, a 2, a 0, and a -2, but they've kind of written them from smallest to biggest. So the smallest one is -2, and then you got 0, and then you got 2, and then you got 4. Okay, and these curly brackets denote a list. Like this is a list of values, basically. So I didn't do them very well, but let me do it kind of nice for you. Okay, they look kind of like that. So this is how you say that you got a set or a list of objects, in this case inputs and outputs, or x's and y's. Okay, now on the next guy, you'll notice that it's not a bunch of points. Okay, so I can't make a list. I can't say, oh, it's -3 and -2 and -1 and 0 and 1 and 2 and 3 and 4, because there's points in between, right? Like what about -1, 2.5 and -1.5 and -0.9 and stuff? There's all of these in-betweens here. All the decimals, all the fractions count in this domain, in this range. Okay, so what they have here is not a list. Okay, here they have a list because there's only a certain, there's only 4 of them. Here there's infinitely many points on this line, and so we can't list them. In this case, what they do is they use an inequality. Okay, so when you're looking at domain and range, what you want to look for is the maximum and the minimum of those values. Okay, so for this one, if you're looking at the maximum value that x is ever going to be, it's like too high, right? Like this arrow keeps going forever. So the maximum value of x is basically infinity, because this arrow is going to keep going to the right. And all these x values count. So like for here, the x value is -3, and for here the x value is -2, and for here the x value is -1.5, and for here it's 0. But it's going to keep going to the right, and all the x values to the right are going to be covered. So what I like to do with my domain and range is I like to start by just listing the maximum and the minimum. Okay, so for this one I'd say max is infinity, and then the min is -3. So max and min, and this is for the x variables, right? Domain is the x values, okay, the inputs. Okay, this is my max and my min for x. And so what I'm going to do is try to write an inequality that says what x can be. So the only boundary I have is that I can't go below -3. So x is greater than or equal to -3, and that's where that came from, right? So -3 works, and -2.9 works, and -2.5 works, and 5 works, and 10 works, and 100 works, but -4 doesn't work, and -3.1 doesn't work. Okay, so we're writing an inequality to represent this. Okay, another way you can think about it is squishing this graph so it's like completely flat. So imagine that we took our graph and we like flattened it, like, and we just squished it. What that would give us it would give us a number line, and we're only interested in the x values. So our number line would look something like this. -3 would be over here, right? We'd have 3 over here, and then our arrow would kind of go like this. It would be like a solid dot here, and it would go to the right. Okay, so that number line is basically the graph of this inequality, right? X greater than or equal to -3. And so you can kind of think of it as taking this two-dimensional graph that has 2 variables, x's and y's, and like flattening it and squishing it so that you're only worried about the x variable. Okay? So kind of putting that all together, the domain of this function is expressed as this inequality. Okay, that is the domain. Now there's another way to write domain called interval notation. Okay, interval notation also uses the max and the min. Okay, you always start with the lowest number, and that's your low boundary, and then you write your high boundary, right, infinity, so max and min. And then if you can include that number, so close dot at -3, that's part of the domain, I'm going to put a bracket, and if I can't include that number, so it's like infinity or something, we're going to put a parenthesis around that. Okay, so there's 3 ways to express domain. The first is the list, right, that we talked about here. Okay, then there's like inequality notation, and then there's what we call interval notation. Okay, I think your book is probably going to use this, but this is also something you should probably know from 9th grade. Okay, let's talk about the range a little bit. Okay, now again, when I talk about range, I always like to look at the max and the min. Okay, so the maximum y value, the highest this graph is ever going to be is 2. Okay, so I'm going to write max 2. Okay, and then I'm going to write the min. Now notice this arrow is going to go down forever, so there's no like lowest value here. It's just going to keep going on and on and on, but in the negative direction. So my min is negative infinity. If I were to take this graph and I were to compress it this way and squish it, so I'm only looking at the y-axis, what you would have is kind of a vertical number line, and you would have, 2 would be up here, this would be 0. You'd have a closed dot here, and then it would go down, right, forever and ever and ever. Okay, and this is 1, 0, -1, right, that kind of thing. So squishing our graph so we're only concerned about the y values, right, is going to give us like a vertical number line that looks like this. And we can write that as an inequality, right? This is y, the y value, is less than or equal to 2, right? I wrote it wrong. Less than or equal to 2. Less than. Because it can't be bigger than 2. It can't be 3, it can't be 4, right? Our graph never goes above 3, or it never even really goes above 2, okay? So this is the range as an inequality. Now, if you want to write that in interval notation, again, you go min-max. I'll start with the smallest. So the smallest value is negative infinity. The largest value is 2. And then if we're going to include the piece, we put a bracket. So we're including 2, right, closed dot. And then we'll put a parenthesis around the negative infinity. We actually always put parentheses around infinities because they're not really numbers that we can include. They are more of a concept. Okay, so this is your range. And you can kind of see that here, right? So domain, range, and domain and range. Discrete versus continuous. Okay, continuous, again, is infinitely many points, so you don't write a list. You write an interval, basically, either using an inequality or using interval notation. Okay, the cool thing about this book is they have this, like, try this kind of thing. So they give you an example 4, like this is an example, and they're like, okay, now you try it. Let me zoom out here. And then you can, figure out if you know what you're doing. Okay, so it talks about discrete functions here and continuous functions, right? Like this is discrete, this is continuous, and it asks you to practice. And the cool thing is the answers to these try this questions are in the back of the book. So if you're trying to learn on your own, you can check. So let me show you that really quick. If you go to page 1010 in your book, you will see that there's answers for lesson 2-3. So here's the first try this question on page 104. Here's the try this question on the page that we're on. So notice they have the domain and they have the range for the discrete graph and then also for the continuous graph. So this allows you to kind of practice using the example that they gave you and then check to see if you're right. Okay, so that's kind of how domain and range works. Let's go back to our current page. So again, there's the try this question. Right? You can see the answer to that in the back of the book to make sure you're on the right track. Okay, now going back to your book here, okay, it says in your homework, the problems you're going to do a few of these guys. State the domain and range. Okay, well, it doesn't give you a graph, but that's okay. The domain and range, the idea is the same. The domain is all possible x values, and the range is all possible y values. Okay, so looking at our problem here, 37. What are all the x values? Well, that's an x, or an input, and that's an x, or an input. Okay, so the domain is the list of all possible x values. In this case, that's 0 and 3. There you go. That's domain. Okay, for range, we want all the possible y values, or all the values of the output variable, in this case 2 and 4. We want to put them in order, and if the same number is used more than once, we don't repeat it in the domain and range. We don't list it more than once. Okay, so there's your domain and range for 37. You can do 38, 39, and 40, but remember that if there's any repeats, you don't list it in the domain more than once. Okay? So those aren't too bad. Another place you're going to find domain and range is in some of these graphs. So you have a few graphs to do. It says graph each function and then state the domain and range. So we'll get to that in a minute, but what I recommend that you do is use desmos.com, or you can use a graphing calculator to kind of see what those functions look like, and then you can sketch a graph and figure out what the domain and range is from the graph. So you'll need something to help you out graphing those probably to make sure you got the right thing. Okay, we'll come back to that in just a minute. In fact, I'll make a separate video because I need to pull up Desmos so you can see what I'm doing. But before we end this video, let's jump in here and talk about evaluate and function notation. Okay, evaluate has the word value in it, right? Notice, value, right? So when you see the word evaluate, what that word means is give me a number. Okay, plug in a value for x and give me a value for y. So let's take a look at one of these here. Let's look at 45 real quick. Okay, and see what it's asking. So we have this function, g of x, okay, and this is written in function notation, so that g of x means a function in terms of x, and its name is g. And we want to evaluate it for x equals -1, and then x equals 1. Okay, so what that means is plug that number into the function. Okay, this is how function notation works as a review. Okay, so we want to find g of -1. What that means is take -1 for your value of x and plug it into the g function. So what we do is we plug it in here and we plug it in here. Okay, now the left side of this equation is just a label. It's just reminding us what was the input we used and what was the name of the function. So this doesn't change at all. This stays the same thing. And but what happens is on the right, we actually do the operations and get a number. So order of operations here, this is a grouping symbol. This division is a grouping symbol. So we need to do everything on top first. Okay. In this case, we have a 2 times a -1. That's -2. We're going to subtract a 1 and then divide all that by 1. Okay, so we still have to do the operations on top before we divide. So this is going to be -3 over 1 and simplify. Okay, so what we have here is g of -1 equals -3. This is our final answer for the first part, and there's meaning behind this. So this is the input, I put it into the g function, and this is the output. Okay, so this is the value that you get out of the g function when you plug this in, and that's what the function notation means. Okay, now we also need to do the same thing for this, x equals 1, and so what we want to find is g of 1. Okay, so we plug 1 into the g function. Sorry, I need to go back. I wrote this function wrong. Sorry, let me fix that for you. So the original function was 2x minus 1 over 3, excuse me. So let's change all these to 3's. So we did the right idea, I just had the wrong number on the bottom. So 2 times -1 over minus 1 over 3. So here we are, -2 minus 1 over 3. That's going to give you a -3 over 3, which gives you a -1. Okay, so g of -1 equals -1. So the output's -1, and the input was also -1. Okay, sorry about that. That was my bad. Now let's do the same thing with the input of 1, because it wants us to do it for both of them, right? So plug in 1 into the g function, and you're going to get 2 times 1 minus 1 over 3. Okay, so now the left-hand side doesn't change. Remember, this is just a label that reminds us we're plugging 1 into the g function. The right-hand side is what we want to kind of simplify now, or really evaluate. So 2 times 1 is 2, right? Then we have a minus 1 and a divide by 3. Order of operations is important here. Okay, so 2 minus 1 is 1, so we get a 1 over 3. So g of 1 is equal to 1 over 3. Okay, and the function notation means I plugged 1 into the g function, and my value that I got out was 1/3. Okay, Over here, when I took -1 and I plugged it into the g function, my output, my value was -1. Okay, so that's what evaluate means. And if you need an example, some more examples of evaluate, you can go back and take a look at example 5 in your book, and it shows you what's happening here. So evaluate this function for x equals 4. What that means is take 4 and put it in the function, right? Use the order of operations and then find out what the output value is. Okay, you want to do the same thing with 2.5. It also shows you a graph just as a check, so you can see that that's actually the case. Okay, so that's what evaluate means. In the next section, we're going to talk about, domain and range again, and we need kind of graphs to do that. So tune into the next video because I'm going to record it a different way. I'm going to do a screen capture so I can show you what I'm doing in Desmos. Okay, thanks for watching.